Hello and welcome to a new uniTFTDesigner video tutorial. My name is Jonas and I'm working for Electronic Assemblies development team.
Today's topic is an overview about the different macro types. Macros are functional blocks. They can include graphical as well as programmatical commands. Example given, place a formatted text that shows a recalculated analog input value. The types are screen, normal, and touch macro, process and second macro, as well as I/O port and bit, analog, and RS-232 macro. But in the end, the uniTFTDesigner only makes a difference between screen and normal text macros. The screen's design and the normal macros create the logic behind. Let's look at the whole thing in the practice in the designer. The goal is to create a project that starts a countdown with a keystroke. Visualize an analog and digital inputs. Furthermore, data arriving from the serial is displayed in a window. Let's start with the countdown to explain the process macro and the second macros. We place a formatted text label, change the font, and change the format and the parameters to our needs. We need a touch button to start and stop the timer. Therefore, we need two new macros. As I will connect to a button, I give them a name starting with TM, which is an indication for touch macro. To connect the macros, we just need to modify the macro parameters in the object editor of the button. By the way, I give the button and the label a better name. We start with a simple second countdown. Again, I create a macro, give it the name second macro timer. Till now, the macro is a simple macro. In the button start macro, I define the second macro. The command needed is macro define second. As parameter, we need the name of the macro that we want to call. Last but not least, we need a value that is counted. In the start macro, we set the variable register integer 0 to the value 5. In the second macro, we output the time and decrement the value. If the time is 0, we need to call our stop macro. The command is macro run conditionally. The stop macro deletes the second macro definition. The command needed is mcd. The parameter is this bit field. As you can see, to delete the second macro definition, the bit in the mask is 0. So I need to give the value 1 as parameter. Let's test the second macro. I deploy to simulator and press the start button. The countdown starts. In the register view, we can watch the variable decrementing. Also, stopping the counting is possible. We go back to the designer and change the second macro to our next topic, process macros. Instead of using the command mds, I define a process macro. The parameters need a process number. We can run 10 in parallel. We use process number 1. The next parameter defines the time. I think a 100 millisecond timer is a good choice. There are additional parameters, for example, if you want to call different macros typically. but we don't need that functionality here. As the time base changed, we need other initial values. I load register 0 with 500 as time base is 10th second to achieve our 5 seconds from the last sample. In the timer macro, of course, a simple decrement of the register will not work. I add a calculation to subtract 10. Stop the execution of the process macro, we can use another command. We can change the process time and set it to 0 for stopping. I only adapt the label to 3 digits and start a simulation. As you can see, it works like a charm. I switch back to the designer to move on to the next task, the analog macros. To visualize, I place a bar graph together with a formatted label. I want to display the analog input in volts with 2 fractional digits. The end value of the bar graph needs to be full scale of our 12-bit analog input. I also rename the 2 recently built objects. I create a new macro named AM Analog 0. First, I add the command to set the bar graph. I can simply use directly the bit value. For the label, I need to do some simple math. Pay attention that I use command variable register float to store the float value in register 10 and update the label. Next step is defining the analog macro. On the start button, I add command macro hardware analog using channel 0. The parameter type defines the condition when the macro is called. I want every change on the analog input. The last parameter is the macro name itself. The stop macro needs to delete the analog macro, so I use the in the meantime known command mcd. The bit field is 16, so hex 10. To test in the simulator, I simply press F6. Changing the analog input does not change the values on the screen as long as the start button is not pressed. If you press stop, the changes are ignored again. The next topic is port and bit macros. Therefore, I place 2 labels. On the left one, I want to show the status of the pin connected to the so-called bit macros. The light label shows the port status of port 1. I want hexadecimal output. Of course, I need 2 macros again. The port macro just reads in the status of the port and changes the formatted text. I first code 1-bit macro, setting the label to high. I just copy this macro and rename both with appendix high and low. In the low macro, I change the text to output low. We need to define the bit and port macros in our start macro. The first thing I have to do is setting the first 2 ports as output. Then I connect the falling edge to the corresponding macro. The same for the rising edge. The last command is connecting any change on port 1 to our port macro. I start the simulator with F6. I press the button Start so the I/O macros are active. I change bit 0, the label alters between high and low. Changing the other pins, nothing happens, till I change one on port 1. To complete the sample, we need to add the clearing definition in our stop macro. Only the 2 bits 4 and 8 must be ORed. The very last macro type is the serial RS232 receive macro. I add a macro and give it a name. Unlike before, the macro can be assigned in the project properties. I read in all available bytes to string register 0. The command ypa outputs that string in the terminal window. For testing, we start the simulator and change the COM settings. I go to File, set COM port, and connect the master interface to my physical COM port 2. As sender, I use our demo pack Connie. It contains a 2.8-inch uniTFTS 028-ATC with an interface board with integrated level shifter. As you can see, I connect the serial port of my PC directly with this flat cable. After pressing Send, the data is sent out and received in a simulator.
I hope you enjoyed today's uniTFTDesigner tutorial. Maybe you have time and play around a little bit with our other sample projects and enjoy our video tutorials.